dimensionless. That's not exactly the same idea of yesterday, okay? What I want to do is just to define new variables from the starting one, and these new variables must be dimensionless. What's the idea? The idea is that then these new variables could be in some range, like for example, typically the range where these new dimensionless variables are is either in 0, 1 or in -1, 1. And you can understand why. So the idea of scaling is basically due to two fundamental things. The first one, what you want to do is to look at the equation and try to understand what are the terms in the equation which you can discard with respect to all the other ones. So imagine that you have an equation with, I don't know, 10 terms, okay? So if you can define the equation in terms of some dimensionless variable, you can easily understand if there is any term of these 10 terms which is smaller of all the other ones. So you can discard it, you can forget about that. So this is one of the motivation. The second motivation is basically due to the attempt to allow perturbation. So if I'm able to write my equation in this new dimensionless variable, eventually I can see what is the small term between all the terms of the equation, and I can try to do some perturbation around some equilibrium, around some point. That's actually why you want also the dimensionless variable usually, typically, in the range 0, 1 or -1, 1, because there you know that well, modulo some analytical properties of your function, you can expand in Taylors. So the typical example, the easiest example for understanding why it's important eventually to define dimensionless variables and in terms of some new characteristic quantities is given, for example, by time. Okay, consider time. So imagine that you are describing some process which is incredibly slow. So imagine that you are describing, for example, how a glacier is ghiacciaio. A glacier is moving with time. Is retracting or advancing with time, okay? And imagine that I'm using seconds for describing this process. Of course, this is completely out of mind because this is a process which is extremely long. Using seconds would be completely wrong. Instead, imagine that I'm doing another thing. Imagine that I would like to describe instead some phenomenon like, I don't know, some nuclear reaction. And again, if I'm choosing the time scale to be seconds, this would be again wrong because a nuclear reaction happens in something like microsecond. So if I'm using seconds, it means that I'm using some scale which is larger and larger than the typical scale where this kind of phenomenon happens. So the idea for considering some dimensionless variable then is try to find some characteristic variable where this characteristic variable should be somehow related to the dynamics of the system that you are considering. Okay. For example, if I would like to imagine that I have an equation which is describing the evolution of the glacier, and another equation which is describing the evolution of some nuclear reaction. I would like to make these equations dimensionless. Okay, so I would like to make time dimensionless. What I can do is try to isolate some characteristic time, which in the case of glaciers could be, I don't know, years, for example, decades, and divide by these years or decades. In the case of the nuclear reaction, I have time, and I have to divide by some characteristic time. In the characteristic time for the case of nuclear reaction, we say that could be, for example, microsecond. is not even less than microsecond. Then what I will do is to divide by some microsecond characteristic time. And this way I can making my equation dimensionless. Let me give you some practical example to see how this works with some problem. I will consider the problem of population growth. So the idea, the typical model that describes the easiest model that describes this the growth of population is the Malthus problem. Yes. Something similar. We have seen something similar in the very first lecture of this course. So the idea is that you can write some kind of balance equation for the population. That's actually the same of mass balance equation or energy balance equation. So it's a conservation equation for the population. So the rate of change of the population, some dp in dt, must be equal to the difference in flow of the population, so the population which enters in a region minus the population which exits the region, plus some creation and destruction of population inside the region. So let me suppose that in this model, this Malthus model, the region, suppose that the region is closed, which basically means I do not have flow of population that can enter the region or that can go out of the region. So no flow. The only thing that I can have is creation, destruction of the population. Let me suppose that this term, this creation or destruction of the population, is proportional to the population itself, which is something that you can imagine. So imagine a population, human population, you can imagine that the human population changes, the rate of the destruction and construction of the population could be proportional to the population itself. So I will write this term as R times P, where R is some constant which has dimension of, can you imagine what dimension must have R, looking at this equation? If I look at this equation, what's the dimension in your opinion that could have R? There at home also, you can answer if you know. 1 over time, it's time minus 1. Yeah, that's correct. So this is a very simple differential equation. It's first order differential equation, ordinary differential equation. And you probably know what's the solution of this equation, but if you don't know, let me remind you, this is P naught times the exponential of R times T, where P naught, P0, is the population at the time T equal to 0. Now, the big problem, which was also a social problem at the beginning of the century, was the fact that this Malthus model forecast an exponential growth of the population. So people were doing a lot of social studies to understand what could happen if at a certain point the human population is going to explode with this exponential growth. Actually, the growth is not really exponential. You can include some term in your equation to have a better model of reality. So that's actually how modeling, mathematical modeling works. If you see that your model does not give you some reasonable prediction, you are trying to modify the model, modify the equation to include some other terms that could help in having a better better prediction of reality. So you can include what's called a competition term, and what you would have is the following equation, which is very similar to the previous one, with the only difference that I'm including, oops, the only difference in which I'm including terms, which is minus p squared over k, which is basically, I'm including here on the right hand side a minus p squared over k, so that I can put outside r p, and I will have in parentheses this p over k. This model is called the logistic model, and the quantity k is what's called the carrying capacity. So what is the idea, the meaning of this extra term which is including in the logistic model? So the idea is that I'm introducing some competition. Okay, so imagine that I have a population of pigeons in some closed environment. I say that, all right, that's fine. Pigeons are just having babies, so they increase the number of pigeons with these terms here. But since I'm in some closed environment, there will be some competition in the food, for example, or in the space that I can occupy. So this kind of competition term must, of course, be proportional to p squared, to the population squared. Okay? Because imagine that I'm in competition with you, so I'm part of population, the first part of the population, you are including the other factor p of the population. Since we are in competition for the food that is there, I will add at this term, this extra term, which is going like p squared. So what happens when p is equal to k? When p is equal to k, the term in parentheses is 0. It's 1 minus 1. It's 0. So this means that the right-hand side of the equation is 0. And this means that the growth rate will be 0 as well. So the idea is that as much as p, the population, is growing, as much the second term, the competition term, is limiting the growth of the population. Now, the idea now that that I would like to employ is to try to find some kind of dimensionless version of this equation. Not in the sense of yesterday, not in the sense of the pi theorem, okay? I just want to start from this equation here, from the logistic model, and to find the equivalent equation that we expressed in terms of dimensionless variables.
Sorry, Prof.
Yes.
Only a question. The carrying capacity is a constant or a
The carrying
variable?
capacity is a constant.
Okay.
Well, in the basic, in a basic model, it's a constant. In reality, what you can do in order to make these models more and more difficult is to make some of these constants dependent from other parameters. Okay, so for example, you can make the constant to be, instead of constant, dependent from time or from the population itself. In terms of carrying capacity, in any case, I think it's always considered to be constant, because of course the idea, well, at least constant with respect to the population. So then what I would do is to define some new dimensionless variables which should make the role of time and population. So I want to get rid of time and population from the logistic model, and I would like to express the logistic, the equation that describes the logistic model in terms of this new dimensionless variable. Now, the new variable, as we have seen for time, what I can do is to identify some characteristic scale for the problem. So what I have to do is to identify some characteristic time and some characteristic population in terms of which I can describe now, I can write down the new dimensionless variable. And in order to do this, what I can do is to look at the equation and say, oh, what are the constants which are in my equations? Here I have basically two, in the problem I have three constants. So one constant is this R here. A second constant is the carrying capacity, this K here. And the third constant is given by the population at time t equal to 0. Okay, so it's the initial value of my problem. So I have these three constants. I have to build then two new dimensionless variables using this constant as characteristic scale. For what regards time, that's actually more or less easy because there is just one constant which depends on time, and that's R. Because as your colleague says before, R goes as the dimensions of t to the -1, time -1. So I can define a new time, which I will call tau, which is going to be my, let's say, dimensionless time. It's not a time anymore. It's a dimensionless variable which I obtain as R times t. Okay? T is the time. R is this constant here, which goes like time to the -1, which has the dimensions of time to the -1. For what regards the population scale, so I want to define some dimensionless population, capital P. So what's what I have to do is to divide population by a term, by a constant, which has dimensions as well of population. What exactly is R? R is basically this constant, it's a number, which is expressed in time to -1, which is telling you which is basically telling you how the rate of the growth of the population depends on the population. So I'm assuming that this rate in the easiest case depends on the population. For example, let me put it this way. Imagine that this R is telling you what's the percentage of kids that you are having in a population of human in terms of the population. So imagine that we are 1 million of people, and suppose that every couple is having X kids. This R here is telling you some information about these X kids that every couple is having. So back to the identification of the dimensionless variable. So I wanted the dimensionless variable also for the population. And this variable can be obtained as the ratio between the population P small, which is the real population, and another a constant which also has the dimension of the population. Now, the dimension of the population, there are just other two constants in my problem, and both these constants has the dimension of the population. So both P0 and kappa, this K, they have both the dimensions of the population. So in principle, I can choose either one or the other. I'm just choosing K because that's what I have in my notes. You could choose P0, that would be the same. In any case, let's choose K. So this quantity here, it's P over K. It's going to be a new variable, which is this capital P, which expresses basically the population in a dimensionless way. So this small p here has the dimension of number of people. This k here has a dimension of number of people again. This p here is dimensionless, it's not dimension number of people. Okay? So in terms of this new variable, we can rewrite the logistic equation as follows. So the logistic equation is this one. Let me write here the logistic equation. The P in the T is equal to R times P small p times 1 minus small p over K. So what I'm doing now is to divide both sides of the equation by K times R. So basically I'm multiplying by 1 over K times R, and the same on the right hand side. Now what do I have? I can simplify this R and this R, so that on the left hand side I have 1 over K times R, the P in the T. Note that K and R are both constant. Okay, so I can I can move this R well, in reality, what I can do is the other thing. I can differentiate this equation here, which describes the new dimensionless parameter tau. So the tau is going to be, since R is constant, is going to be R dt. So for this reason, the thing that they have here, R times the t, is equal to the tau. So this thing here is going to be 1 over K the P the tau. And I can do the same thing also for this other equation. So if differentiating both sides of definition of capital P, what I obtain is the capital P is equal to 1 over K times the P. So this means that this 1 over K, the P, is exactly the capital P. So the quantity which is on the left hand side of my equation, this thing here, simplifies in the capital P in the tau, in the new dimensionless variable, which is more or less describing the evolution in time. Let's see what happened to the right hand side. The right hand side is quite easy because I have P over K here, which is capital P, times 1 minus P over K again, which is again capital P. So at the end of the game, what I've done is to rewrite the logistic model in terms of dimensionless variables, so a dimensionless population and a dimensionless time. And now the logistic equation looks very simple. Indeed, you can solve this with this can be solved by separation by separating the variables. And I will leave to you the honor to prove that the solution is this one times the exponential of minus tau, where alpha is defined as P naught over K. So basically is capital P in 0. Now, note also some other interesting fact from this equation, which is something which will be interesting for the second part of the lecture today. Note that the limit for tau that is going to infinity of P of tau, what's the limit of tau that's going to infinity? These terms here are going basically to 0, so you will remain with alpha over alpha. So the limit of capital P of tau for tau that's going to infinity is equal to 1, which basically means that for tau that's going to infinity, small p is reaching the carrying capacity. Note also another thing, that the equation written in the logistic equation written in this way has two equilibria. The equilibria are those points that are defined when the rate is equal to 0. So are those points defined from the right hand side of this equation equal to 0. Are the points that are defined by P, capital P times 1 minus capital P equal to 0. This equation, so P times 1 minus P equal to 0, has two solutions. One is capital P equal to 0, and the other one is capital P equal to 1. So, in particular, would like to concentrate, just to say comment on this capital P equal to 1. This is what is called an attractor. Why? Because capital P is equal to 1 is exactly the solution to which you are approaching when you are considering the limit tau that is going to infinity. So when you are considering this dimensionless time that's going to infinity, you are approaching the point P equal to 1. That's actually why this is called an attractor. This is attractor. And this is independent of alpha. So it's the independent of the starting point. Does not depend on P naught. Okay, great. Now, I hope that this tells you, gives you an idea of why getting some dimensionless equation from a dimensionful equation, it's some nice thing, because basically you can have equations which are easier to solve. Let me give you also a second example, which is
Sorry.
yes.
Only a question. So P is between 0 and 1, as all the values between 0 and 1, or no?
Capital P, you mean?
Yeah, capital P.
Capital P is gonna be so if tau is gonna be, this is alpha and the capital P depends on P naught and K. You can have some oscillation around the value of P equal to 1. So the carrying capacity here, you are not allowed to say that capital K is larger than P naught. I can start with some P naught which is greater than 0. If this P naught, small p naught is greater than 0, this means that the terms of the logistic model, which is on the right hand side, would push the population toward some equilibrium down, which is the equilibrium that then you will reach with capital P equal to 1.
Okay, thank you.
I don't know if, okay, let me put in this other way if it's not clear. Consider the equation which is describing P. So this P of tau, okay? And let me consider in particular the tau equal 0. So tau equal to 0 means that this things here is equal to 1. So alpha simplify with this minus alpha, and you get P of 0 equal to alpha, which is exactly this thing here, okay? Now this alpha, this, or if you want in other words, capital P in tau equal to 0, is equal to this ratio, to the ratio small p in t equal to 0 and k. They are both constant, but let's say that they are independent constants. They do not talk each other at this stage. I can choose P0 to be 1 million and K to be 1,000. Okay? What does it mean that K is equal 1,000? The carrying capacity, remember, is basically tells you what's the maximum amount of population that the region can hold. So basically means that I'm in a region that can just give food to 1,000 of people. But the P naught, which is the starting population, is 1 million. So the logistic equation tells me that is including these terms in minus p squared rp squared over k to tell me that I'm starting with 1 million of people. But this number, as tau increase, is going down toward the value of 1,000, toward the value of k. So it's going down in such a way that this p at tau that's going to infinity is going to 1. Okay?
Yeah, okay.
All right. All right, in the new problem, instead, what I would like to consider is some example which is a bit more complicated. I want to consider this example for a simple reason. As I told you in the introduction, the idea is not just to write the equation in a simple way. The idea is also trying to understand if there are terms inside the equation that can be discarded with respect to other terms because they are small. Okay, this is something that we will use in the future when we will do perturbation theory. So, and I would like to offer you this new example. Again, you can find this example in the book by David Logan. So this new example is nice because gives you an idea of the fact that you must pay a lot of attention in choosing the right characteristic time, the right scales, the right characteristic times, and the right independent dimensionless variables. So the example is very easy from the physical point of view because it's the example of a projectile, some body that I shot in the air with a gun. So imagine that I'm this one, I'm on the earth, and I'm launching a projectile upwards with some initial velocity v. So this is the initial velocity v. The projectile is this point mass with mass m. This is the height h of t at which the body is at the time t. And then here I have the Earth, which has a radius here, which is given by capital R. And the Earth, well, I'm supposing that the Earth has mass equal to capital M. So this is Newton's law. This is very easy, and you know very well that this is, well, F equal M times A, so M times the squared of H of T in the T squared. And then law of the gravitational interaction was this thing. This is equal to minus G times M times capital M, small m, divided by the distance between the two bodies. Yeah, exactly. So this is H plus R squared. Okay? Because I'm supposing, well, as you probably know, when you're considering this kind of problem, the mass of the Earth is supposed to be concentrated in the center of the body, in the center of the Earth in this case. Okay, great. However, I know that when h is equal, when h is equal to 0, I know that this term must be equal to what? To minus m times g, right? Where this small g is the gravitational acceleration, is the 9.81 meters so on per square second. So what I can do is, since this thing here at h equal to 0 is equal to this, I can simplify this and this, minus and minus becomes plus and plus. So what I can say is that I can write g times capital M as the acceleration small g times r squared. So that I can get rid of the capital M because it's difficult to measure the capital M. I get rid of the capital G because I don't want to measure the constant capital G. And what I get if I'm using this relation here, the Newton law becomes m the squared ht the t squared equal to minus r squared over h plus r squared times small g times small m. Fantastic. I can simplify the small m on the left hand side and the right hand side. So this is the differential equation which is describing this this motion, the motion of the projectile. There is one further ingredient, well, two further ingredients that I need, and these ingredients are the initial conditions. So the initial condition is the height of the projectile when it's starting. I'm supposing that the body is starting at t equals 0 with h equal to 0, so it's starting from the ground on Earth. Then I need another thing, which is the velocity. So the h in the t calculated when t equal to 0. And this is one of the data of the problem, which is, I assume this to be capital B. Okay, great. Now let's try to do the exercise that we have done already yesterday. So let's see what happens if I'm using dimensional analysis. What can I learn by using dimensional analysis? So, what are the variables, the dimensionful variables of the problem? Well, I have time, which has the dimension of time. Then I have the height of of the projectile, the height of the body at time t. This has the same dimension of the radius of the Earth, and this dimension, of course, is a length. Then I have, what do I have still in my problem? I have the velocity, starting velocity, which has dimension of L times t minus 1. What do I have more? Well, I have g, small g, which is an acceleration. So I have dimension of g equal to length t minus 2. Correct. So what we want to do is to find, you remember the pi theorem yesterday, the Buckingham's theorem. We want to find some pi's, which are some dimensional combinations of all these variables. So of t, h, r, v, and g. So the idea then is that pi can be written as a combination of these. So I can write pi as t to the power alpha 1, h to the power alpha 2, r alpha 3, v, this v is velocity, remember, it's alpha 4, g alpha 5. And then I'm supposing that this pi is dimensionless. So the dimension of this must be equal to the dimension of the other one. Okay. Now, do you remember what's the idea now? The idea is that I rewrite the dimensions of all these quantities, these variables which are on the right hand side. Before arriving there, I have to write t as capital T, this is to the power alpha 1. H is a length to the power alpha 2. R is a length to the power alpha 3. V is length times time minus 1. This is then L alpha 4, T minus alpha 4. And G is L alpha 5, T to the minus 2 alpha 5. Now I can match the things on the left hand side and on the right hand side. So this is giving me, for example, let me consider time. So this tells me that alpha 1 minus alpha 4 minus 2 alpha 5 is equal to 0. And then when I consider length, I will have alpha 2 plus alpha 3 plus alpha 4 plus alpha 5, all these equal to 0. Okay, so what I have to do is to solve this linear system. Okay, note, can you tell me, just looking to this linear system, what's the rank of the system? The rank. What's the rank of the matrix of the coefficients of this system?
Does make a third equation?
No. What I can do is just to write the matrix of the coefficients of the system. This is 1, 0, 0, minus 1, minus 2, and then I have here 0, 1, 1, 1, 1. Full stop. So what's the rank of this matrix? Yeah, that's correct, because I have these two columns which are independent. So since I have, since the rank of this matrix is 2, this basically means that there are, I have 5 starting parameters, 1, 2, 3, 4, 5, okay? But this matrix has rank 2, so I have 5 minus 2. This is the number of independent pi's of independent dimensionless variables pi's that I can find. Okay, I can find these pi's. I can find these independent alphas by solving this system. I'm not going to solve this linear system. This is very easy. I invite you to solve in any case to find the 3 independent vectors, 3 independent solutions of this linear system. Okay, so if you're using this, I can tell you that how they should look like. This should be 0, 1, minus 1, 0, 0. The second one should be 1, 0, minus 1, 1, 0. And then the third one is this is 1, this is 0, this is 0, and then this is minus 1/2, and this is minus 1/2. Not sure this, but check if this result is correct. Okay. So once that you find these are the 3 independent, again, 3 independent solutions of this linear system. Okay. These 3 independent solutions correspond to 3 independent variables, 3 pi's, 3 independent dimensionless variables. So basically the first one will correspond to what? To pi 1. Remember what's the form of pi? Pi is t to alpha 1, h to alpha 2, r alpha 3, what's the other one? V alpha 4, G alpha 5. So what's gonna be pi 1? Here alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 are gonna be these numbers that I have in the first solution. So what I will have is t to the power 0. No, 1. 1. H to the power 1, which is h. R to the power minus 1, which is this, and then V to the power 0, which is 1, and G to the power 0, which is 1. So I end up with this expression here. My pi 1 is equal to h over r. Now, employing this vector, I will find also pi 2, which is t divided by r divided by v. And employing this other one, I will find pi 3, which is equal to v divided by the square root of g times r. Now, if I'm using the pi theorem tells me that imagine that there is a relation between T, H, R, V, and G. So between the dimensionful parameters of my problem. So my physical law is described by this F of T, H, R, V, G equal to 0. So my pi theorem tells me that this law here can be equivalently described by the equation, let me go capital G, of what? Of the pi's, right? Pi 1, pi 2, and pi 3. So suppose that this is just an algebraic or transcendental equations. This means that I can, let me resolve this equation with respect to one of the pi's. So let me suppose that I'm able to resolve this equation with respect to h over r, for example. So what I get is h over r, which is gonna be some function g tilde, let me say, of t divided by r divided by v, and v divided by square root of g times r. Now this is an expression which tells me some relation between all these quantities, and that's already a nice result, because basically, for example, I can try to understand what happens, what is the maximum time, how is the maximum, the time when the body has reached the maximum height, how does this time scale? So what I want to find is what's the behavior of Tmax, where Tmax is the time when the body reaches the highest point of its trajectory. Okay? What kind of estimate I can do for finding this Tmax? Well, by definition, Tmax is the time when the point reaches the maximum height of the trajectory. What's the velocity in that point? What's the velocity when the body has reached this maximum height?
0.
Very good. Then what I can do is to take this expression to derive this expression with respect to time, because in this way I will have 1 over r, the radius of the Earth is not changing, is a constant. Then I have dh in the t, and this is going to be evaluated in T max, right? And this thing here is equal to 0. On the right hand side, in any case, I will have the derivative with respect to time of g tilde, which is a function of t r over v and v over the square root of g times r. This is also evaluated in some T max. Okay, now I'm not interested at all in what is the exact form of this new function here. So this is a derivative of a function which will be another function. Let me call this new function some g tilde tilde, g double tilde. I don't care about what's the form of this g double tilde. The only important thing is that this g double tilde is some new function which depends on a variable which is T max over R over V. So I will solve this new equation in terms of these, what I will find is this thing here. So let me repeat. I don't need this one, yeah. So basically, this derivative evaluated in Tmax is going to be some other G tilde tilde of T max over RV V over square root GR equal to 0, because this is equal to 0. Okay? But now this is just, again, let me suppose that this is some equation which is either algebraic or in any case some transcendental equation. This means that I can solve this equation in terms of one of the variables. Let me solve with respect to Tmax over Rv, and that's what I wrote here in this equation, in the last equation. So what I can tell without basically without solving the equations, because I'm not solving the equations, again what I'm doing is just some analysis of my model. What I can say is that the maximum time, the time of the maximum height reached by the body, by the projectile in its trajectory, must be somehow a function of is a function of v over the square root of g times r. So this T max must depend on v over the square root of g times r in this particular combination. Okay? So this is the result that I can, to which I can arrive doing just the dimensional analysis. So with the techniques that we have seen and we have studied yesterday. Now, mosquitoes. Now, let's see what I can do instead using the techniques of scaling. So let's see what I can say if I'm using the scaling procedure that we have seen today in the last hour. So what I have to do is to define some characteristic time and a characteristic length. So I have suppose that I have some t tilde, which is equal to time over the characteristic time tc, and then I have h tilde, which is dimensionless height, which is equal to h divided by some characteristic height hc. Now this tc, t with c, and h with c are two characteristic scales that must appear starting from the constant that I have in my problem. Remember, my problem is given by this equation. What is the equation? So this equation here with this initial data. Okay. So I have basically two independent variables which are h and t. And I want to make h and t dimensionless. And to do this, I will divide by a characteristic time and a characteristic eighth, which must be some combination of the constant that I have in the problem, which are capital R, small g, and capital V. So what I have to do is to find some combination for Tc such that Tc is a function of V, R, and G, and Hc such that Hc is some function of V, R, and G. Now, there are different ways, different ways to do this, to find this equation. I will show you 3 choices, and well, basically I think that there are more than that. There are more than 3 choices, but in any case, these 3 choices are important because they will show you some important message later. So one choice is, for example, Tc equal to R over V, and Hc equal to R. This way, well, Hc has the dimension of a length, so it's okay. Tc has the dimension of a length divided by a velocity, which is a dimension of time. It's okay, also this one, from the dimensional point of view. Let's see a second choice. Second choice is Tc equal to the square root of R over G. And Hc instead, let me take Hc again equal to R. And then let me consider the last choice, choice 3, where Tc is equal to V times G to the minus 1, and Hc, which is given by V squared times G minus 1. So in principle, from the dimensional point of view, these are all of them well justified, because all the TCs are from the dimensional point of view, they are times, and all the HCs are characteristic scales with the dimension of a length. So from the point of view, exclusively from the point of view of dimensional analysis, these are all of them fine. So let's see what happens when I rewrite, in terms of all these parameters, my model, my equation. So what I want to do is to rewrite this thing here with h not equal to 0 and the h in the t evaluated in 0 equal to v. So what I have to do is to rewrite this problem in terms of some new variables, t tilde equal to t over tc and h tilde equal to h over hc. Okay? So if in the first case, so if my Tc is R over V and my Hc is equal to R, this is just algebra. Let me arrive directly to the equation that I obtain. So in the first case, I will obtain something that's going in this way. Epsilon the squared H tilde in the tilde square and that T tilde squared equal to minus 1 over 1 plus h tilde square, with h tilde 0 equal to 0, and the h tilde in the t tilde evaluated in 0 equal to 1. Epsilon is a parameter which is given by v squared divided by g times r. Okay. What happens in the second case? So the second case is Tc equal to the square root of r divided by g, and Hc is equal to r. So in the second case, the equation becomes the squared h tilde in the t tilde square is equal to minus 1 divided by 1 plus h tilde squared with h tilde 0 equal to 0 and derivative of h tilde with respect to t tilde evaluated in 0 equal to square root of epsilon. And finally, I have the third case. What happens in the third case? In the third case, so in the third case means that I'm considering the characteristic time to be velocity divided by g and the characteristic height to be velocity squared divided by g. And the equation, the dimensionless equation, would become d squared h tilde d t tilde squared equal to minus 1 divided by 1 plus epsilon h tilde squared with h tilde in 0 equal to 0 and with d h tilde in d t tilde evaluated in 0 equal to 1. Now, from the mathematical point of view, all of them are, until now, all of them are fine. Okay, so now let me suppose, in any case, that now I would like to see what happens. I would like to analyze these equations when, in the case when the velocity v is much smaller of g times r. Okay, that means that when this parameter here is much smaller than 1. I want to analyze the situation when epsilon is much smaller than 1. Okay, which is something with it's a kind of problem that I would expect, because I expect the velocity of the body that I'm shutting upwards to be much smaller, well, the square of this quantity to be much smaller of this quantity here, right? Because g is 9.81 kilometers per second, r is the radius of the Earth, guys. So it's going to be surely a parameter which is smaller than 1. Okay, fantastic. So what happens in the three cases? What happened in the first case? What happens in the first case? So what I have to do is basically, since epsilon is much smaller than 1, the idea is that you discard all the terms that are going as epsilon. So basically in the first case, I would have something like 0 equal to minus 1 over 1 plus h tilde squared. If I'm just naively cancelling all the terms which are proportional to epsilon. And let me underline, naively, okay? Because in reality, I'm not allowed to do this kind of passage because I don't know the second derivative of h with respect to t tilde. What's the relation between this second derivative and the magnitude of epsilon? So in any case, naively, I would have something like this. But this object here does not have any solution. So this equation here would have no solution. So let's see what happens instead in the second case. In the second case, I have, well, some equation which is untouched. There is no epsilon term in the equation. The epsilon term appears in the initial value, right? So the initial value tells me that the derivative of h tilde with respect to t tilde in t tilde equal to 0 is equal to 0. okay? But what does this tell me? This, together with this, tells me that this kind of problem is non-physical, because basically here you have the second derivative which is negative, right? So the profile of HT would be the one of a parabola upside down, passing to the condition H0 equal to 0, so something like that, which basically gives me a negative H. Physically, this means that I'm shutting something in the earth. This one is the velocity. This guy here, this tells me that the velocity is going to be 0 at 0. So this means that in this point here, basically it's the object is not even falling. The object, this describes some negative H. Negative H means that I'm going under the ground. So from the physical point of view, so no physical meaning. So, well, meaningless from the physical point of view. Luckily, we have the possibility number 3. In the possibility number, no. All right. In the possibility number 3, yes, some question there? No, all right. So in the possibility number 3, instead, what happens? So my equation here, this equation becomes d squared h, sorry, the h tilde in the t tilde squared equal to -1, with h tilde 0 equal to 0, and with the h tilde, the t tilde evaluated in 0 equal to 1. Amazing. This thing here finally has a solution. And what is the solution? The solution is going to be some h tilde, well, it's the solution of this second order equation, differential equation. So it's going to be some h tilde equal to t tilde minus t tilde squared over 2, which would correspond in the dimensionful world to some h equal to -1/2 g t squared plus v times t, which is exactly the kind of law that you have for describing the motion of a projectile, the trajectory of the motion of a projectile which you are shutting upwards. So, what was the problem in these choices? Why one of the choices is working and the other ones are not working? And this is the very important message of this part. So basically, the problem was in considering. Alphonse, yeah? Oh, all right, okay. So the big problem was in considering this thing here. Why? Because basically what I'm doing is, the idea of my problem is that the velocity is relatively small with respect to the other two constants of the problem. So the velocity is going to be relatively small with respect to the product g times r, the velocity squared. So if the velocity is small, it's completely meaningless to consider the characteristic scale of the length to be something very large. So what I have done here is to say that the characteristic height is equal to the radius of the Earth, which is an extremely large quantity with respect to the velocity v, which is involved in my problem. That's actually why both the choice 1 and the choice 2 are basically wrong, are not good. And this is also the same reason why instead the choice 3 is a good choice. So this choice 3 allows you to take into account the right magnitudes of the variables in play, and allows you to have a good approximation of the problem when the velocity is small with respect to all the other things, which is given by this law here. And I think that we can stop for 10 minutes. We can have a pause of 10 minutes and we will be back at 33.
Doctor, I have a question. Can I ask her?
Yeah, you can ask, please. No, you can. Yeah.
The number 2 that you say velocity is epsilon. Am I right?
In
Yes.
0.
Yes. But on the left side of the photo, d2h divided d2t is equal 0,2. Am I right?
I didn't understand. So what about this? This is untouched. This is the velocity just in one point.
But the velocity is epsilon, that epsilon is equal to 0, and number 2, that's d2h divided to d2t is equal 0,2. Yes?
Is not equal to 0,2, is equal to this quantity here. Is equal to minus 1 over 1 plus h tilde squared. So I want some negative things. This, what I want to say is that this equation here tells me that the second derivative is negative. That's why the second case is not physical. Because for being the second derivative negative means that I have a function which is concave.
Okay, thank you.
All right. You can go out. As I said, there was a pause. You can go out.
Hello, Professor. Excuse me.
Yes, please.
Do we have some reference book regarding this subject and these topics?
Yes, the both the lecture of yesterday and the one of today are taken by the same book, which is from David Logan, and it's called Applied Mathematics.
Perfect. And we will be able to find this book in the library?
That's actually kind of comment that I was doing yesterday. Can you stop the recording another time? I'm sorry. How do you stop this record?
Sure, no problem.
I don't know how to stop recording.